In this chemical reaction, hydrochloric acid is being poured into a solution of sodium hydroxide and indicator, turning the solution a very vibrant pink. Here, the reverse reaction is happening, where sodium hydroxide is poured into solution of hydrochloric acid and indicator, making the solution colorless once again.
Hey Alex, can you explain what happened in that demo for us?
So in our lab, you initially saw a colorless liquid. That was a mixture of phenolphthalein, which is an indicator, and NaOH, so sodium hydroxide, which is a strong base. Phenolphthalein indicates whether the solution is basic or acidic. In basic solutions, which NaOH is, it is a colorless liquid. Then when we added HCl, which is an acid, or hydrochloric acid, the indicator suddenly became pink, and that's because with the presence of acid, phenolphthalein turns into a vivid, bright pink color. At equilibrium, phenolphthalein will show up as a slightly light pink color.
So now on to the actual demonstration. But first, let's talk about the pH scale. Basically, the pH scale is just a measurement of how acidic or basic something is. So 1 through 6 is acidic, 7 is neutral, and 8 through 14 is basic. Now, here's a pH curve of what was happening in the beaker in our demo. So we started out with just NaOH and indicator phenolphthalein in our beaker. So the pH was quite high because NaOH is a strong base. Now, as we added acid, HCl, into the solution, the HCl and NaOH were completely disassociated, meaning they were both in completely 100% ionized with their respective ions. That means the acid and base could effectively neutralize each other. So once there were equal moles of acid and equal moles of base, the solution hit equilibrium point at 7. That occurs only for strong acids and strong bases. If you had a weak acid or weak base titration, that would occur a little bit higher, let's say at 8 or 9. But we had strong acid and strong base. And at this point, at equilibrium point, the indicator turned a light pink. Now we bypassed that in our chemical demo for dramatic effect. We went directly into excess acid where the pH was quite low and the indicator turned a very bright pink. And so because there was excess acid, that means all the acid was used that was needed to be used in neutralizing the base, and we added even more. The indicator flared up and turned a very bright pink. Now in the reverse process, we started out with a very low pH because the solution was very acidic, but we added base. And so that base effectively neutralized the acid, reached equilibrium point again, and turned back up here to a very basic solution where it was clear. The next thing we have to define is what is a strong acid and what is a strong base. The strong, all that really means is that acid or base will completely ionize, 100% dissociate in any solution such as water. Basically, what a strong acid dissociation looks like is for any strong acid, HA, let's define it as, it will turn into H plus and A minus. There's no leftover HA hanging around. The same goes for a base, any rudimentary base, XOH. It turns into X plus and OH minus in a solution. There's no leftover hanging XOH around. So what are the strong acids and what are the strong bases? Well, there are 7 strong acids, and they are HCl, HBr, HI, HClO4, HClO3, HNO3, and H2SO4. There's no other strong acids. There's only 7, and these are it. What is a strong base? Well, basically, the cation for a strong base comes from group 1 alkali metals, or the heavy group 2 alkaline earth metals, such as calcium, strontium, and barium. And those are attached to an anion of OH minus. So basically, we're going to go into an in-depth explanation of what was happening in our chemistry demos and define some of the terms we used in it. So what you saw in our chem demo was just a really quick and easy strong acid, strong base titration in a beaker. So first things first, what is an acid and what is a base? Well, we're going to use the Bronsted-Lowry definition of acids and bases. And basically, all an acid is a proton donor, and all a base is a proton receiver. A proton in this case is defined as H+, or the hydrogen ion. Now, what exactly does a proton donor mean, and what does proton receiver mean? Well, let's look at this chemical reaction. This is acetic acid and water, and it turns into the acetic acid ion and hydronium, or H3O+. So what's really going on here? Well, if you look at the acetic acid, it's donating a proton. It's losing an H+, and as you can see, turning into the conjugate base. And that H+ is being transferred to the water. And the water is acting as a base because it's receiving that H+ and turning into H3O+, or the hydronium ion. So that's all really what proton donor and proton receiver means. So the acetic acid is the acid, the water is the base, the acetic acid ion is the conjugate base, because if you reverse this reaction, it's the one that's gaining the H. And the H3O+ or hydronium ion is the conjugate acid, because if you reverse the reaction, if we go this way, it's losing an H.
Hey, Ermina, can you explain lab safety for us?
Well, of course, lab safety is the most important element of any chemistry class, because there are a lot of chemicals that we deal with in accordance to the name chemistry, and they can be flammable and corrosive, and they can irritate your skin and hurt you. So what do we do to stay safe? Well, I put on lab aprons to make sure nothing spills or gets wet, or anything gets wet on my clothes or on me. And also, you always have to put your hair in a bun or a ponytail to make sure it doesn't catch on fire or dip into HCl. And lastly, always make sure you wear goggles, because you don't want anything into your eyes. And if you do get something into your eyes, immediately run to the eye wash station. Stay safe, children.